The Computer Science 345 Angluin Learning Algorithm Implementation Demo for Brendan Watling 227-49004. First, as you can see, I've already compiled the project, and I'll show you it running with the regular expression AB star. So running it, you can see we have 6 equivalence queries and 19 membership queries, which is exactly what the result given to us in results.txt. Now moving on to the actual implementation. So first we start off with the learner.java and the learn method, which is the main method that produces the S of A that is learned and tests it with equivalence queries against the oracle provided. So after the observation table is initialized, we then check, start with iteration, and that goes up to a certain max. For the BSQ, we'll come back to that later. But first, let's start off. So first, the table is made cohesive, and this calls other methods that were implemented for this project by us, or by me. And then, so that made it cohesive and folded in, closed it, so that it could then be built an SFA from it that could be used as a conjecture against the oracle. Then the conjecture created using the build SFA was then checked by the oracle with an equivalence query, and if no counterexample is provided, that means that the conjectured SFA was correct, and so then returns the conjecture saying that it was good. Otherwise, if there was a counterexample provided, that means that the conjecture was incorrect, and so changes have to be made to the observation table. We'll come back to the BSQ implementation, which is defined by the BSQ flag. So then, the counterexample is then processed by the table, and then the loop starts again back to the top where the table is made cohesive again and a conjecture is created again, and this loop continues until either we reach the maximum number of iterations or a correct SFA is conjectured. Moving on to the make cohesive method of the observation table. So here you can see it initially starts by filling out the table, making sure all entries in the observation table are filled in. And then there are 2 flags: const flag for make sure that it's consistent if the make consistent method made any changes, and the close flag if the close method made any changes. So if const flag is true, then the table is made consistent again. And then if the make consistent method had any changes, then the table is filled again. The distribute method, which was implemented for us, is then used, and if that made any changes, the table must be filled once again. And the close flag is set to true because the table needs to be closed again. So then if the close flag is true, then we close the table with the close method, and then the table is filled if that close method made any changes. And then the loop continues until no changes are made, which are indicated by the const flag and close flag. Moving on to the first method that had to be implemented, the fill method, which is quite simple. Just make sure that all the entries in the observation table were full, and those are indicated by the variable f, which is a hash map from a list of symbols, which are words, to Boolean values indicating whether or not that word is accepted or not by the SFA being learnt. So it goes over all words, W and SUR, which is the union of the sets S and R, and then it also loops over all words lowercase e and uppercase e, which are used as the columns for the observation table, and then it constructs a concatenation of these 2 words as array lists, and then checks if f contains this word, and if it does, then it continues to the next iteration because we already have that entry, it's filled in. Otherwise, we then fill that entry in by doing a put with a membership query for that word against the oracle. Moving on to the close method, which just closed the table and made sure that for every row corresponding to a word in the set R, there's a corresponding entry in the set S that has the same row. So to initialize, all the rows corresponding to words in S are added to the variable S rows, and then all the words in the set R are looped over and contained in the lowercase r variable. And then pretty much if S rows contains the row corresponding to lowercase r, then nothing needs to be done because that row already exists in S rows. And so continue, otherwise we look for a best R that needs to be added to S in order to work with the close implementation. So if best R is null, that means that we never found a previous best R, so then we just set best R to R. Otherwise, if best R is not null, we need to see if the current R we're looking at has the same row as best R and is actually better by being a smaller size word. And this is done with this if statement. After that loop, if best R is null, then no word R in the set uppercase R was found that needed to be added to S, so it was returned false and nothing is changed in the table. Returning false just means that no changes were made. Otherwise, then that best R is removed from the set R and added to the set S, which are both as list objects of symbols. And then evidence closure is handled as described in the paper given to us in the specifications. And then this other stuff was implemented for us already to make sure that everything works out and follows the algorithm explained in the paper that was followed for this implementation. Lastly, the last method in the observation table is the make consistent method. So this just made sure that the table was consistent in that rows, in that words that lead to differing states were actually shown in the observation table rows by adding another column if necessary. So as the to-do explained, you have to find all words W and V in SUR such that their rows so that their rows are the same. But if there is a symbol B such that WB and VB are in SUR, but those rows differ, then we need to find the symbol or the word E in the set E that makes them differ, and then be able to add another column to be able to show that they lead to different states. So this is done by going through all the words in SUR such that the W and V were initialized to the outer loop variable and the inner loop variable, and then make sure, and the way the loop is structured, W and V will never be equal, and then the first check is to make sure that their rows are actually equal. If they're not, to continue to the next iteration. Otherwise they are, and then we get all the words in SUR that contain W as a prefix and store that in W prefix, or contain V as a prefix and store that in V prefix. And the other condition was that the U in SUR must only have one more symbol than W or V. So then once that is done, we technically have all WB and VB in SUR that then we need to check if their rows are different. So we loop over all the all words WB and W prefix, and we get the suffix B, which should only be one character that differentiates W and WB because of how we constructed V prefix and W prefix. And then we loop through all VB and V prefix and make sure that the suffix that differentiates VB and V is actually the same as the B that we got from W and WB. This is just to make sure that they actually share the same suffix character from sigma. And then we store their rows in WB row and VB row, and we check if they're not equal, because if they were equal, then they potentially lead to the same state and we cannot do anything, so we continue to the next iteration of the loop. But if they're not equal, then we need to find out for what symbol or for what word in E they differ on, and then to store the concatenation of B and the symbol in E afterwards. So this is done by going through all the indices of the WB row and VB row and checking for which index they actually differ on. And then we initialize this variable E, which is what wants to be added to the list capital E. And then we add the word that we get that differentiates the two states, and we add that to E to be able to get the BE as described in the paper. And so after the loop is executed, if E is not null, that means that we found a BE in that differentiates two words from the state, so that they lead to different states. And then this is just executing the evidence closure and making sure we add that column, and then we do evidence closure and return true because the change was made. But if E is null, then there was no word found that differentiates any state, so return false because no changes were made. Moving on to the partition function, starting off with the interval partition function. So this just made sure to implement the interval partition function that was described in the specifications. So it starts off with an array list of order objects that contain symbols and the corresponding states, and this was put in order as if it was a number line as described in the to-do that is now marked done. And then the preds array just contained the predicates for each state. So first it started off with handling the edge case from the minimum Boolean algebra symbol to the first evidence symbol by creating an orderer with the minimum Boolean algebra symbol along with the state of the first evidence symbol, and then the loop, over all current words in the order, which is just all the symbols along with their states, the evidence symbols along with their states. And then the predicate for the previous symbol's state is set to the union of that predicate with the interval from the previous evidence symbol to one less than the current symbol that we are looking at. And then to prepare, and this was done using the add and shift methods provided in the partition func class. Then the previous was set to current to be able, because now the new current is going to be set for the next iteration of the loop. And lastly, after the loop is executed, the variable prev will contain the orderer object corresponding with the last evidence symbol on the number line essentially, and then we need to add to that symbol state, the predicate of that symbol state, the union it with itself and the final interval from the last evidence symbol to the maximum Boolean algebra symbol, and then the result is returned as an array list for use in building the SFA. The last base functionality that was implemented was binary search querying, in which case some pre-processing is done before the main loop executes in the learn method, and this was just to add the minimum and maximum symbols to the observation table of the Boolean algebra. And then after the loop, after receiving a counterexample, instead of just processing it straight away and moving on to the next loop, some extra steps were handled after processing the counterexample on the observation table. So if BSQ flag is true, which means that we are running binary search querying, after receiving the counterexample, it is processed and the table is made cohesive again. But then for all the prefixes of the counterexample that were returned from the process function, we do some extra processing to ask more membership queries to be able to determine boundary tuples for the intervals necessary to be able to get more information without asking as many equivalence queries. And this was to, the aim of this was to reduce the number of equivalence queries required for non-optimal counterexamples. So first, if the current prefix is contained in the set S of the observation table, then transition from the prefix's state to the minimum or maximum Boolean algebra symbol was added to be able to to prevent any problems occurring with the get closest method, which say like the current prefix we're looking at is the last evidence symbol we have. This was just to handle those edge cases. So to process the transition from the prefix's state to the minimum Boolean algebra symbol. Although what happened was we made a array or list of symbols that copied the prefix and just added to the end of it the minimum value, and then that was processed, and the same was done for the maximum, and the table was made cohesive again to prevent any state issues. Then the state of the current prefix was gotten, and then the last symbol of the prefix was removed and stored in value, and the state of prefix was stored in index. Finally, the closest variable represents an array of the two closest order objects, which represent the state of a symbol along with that symbol, which was actually the end symbol of a path taken in the SFA being built. So once we had that, as explained, the thing closest, the order of the symbols lexicographically is the closest, the 0th index of closest, the prefix's value stored in value, and then the index 1 of closest. And then implementing the to-do, start off with a prefix order, which was just to mimic the closest orderers, which we have, and this stores the value and the index, which is the state of the prefix. And then the Boolean first was just to indicate if it's we're looking at the left interval between closest 0 and the prefix order, or if we're looking between the interval between prefix order and closest 1. So then going through each order and closest, we have a lower and upper orderer, so that's just to indicate the lower and upper bounds of the current interval we're looking at. So if it was first, then we're looking at the left interval, so we set lower and upper accordingly. Else we set lower and upper in the other order, in order to know that we're looking at the right bound, the right interval instead. And then first is set to false, because after this executes the first time, we're no longer looking at the left interval for the next iteration, but the right interval. So if the states of the lower and upper bounds of the interval are the same, then we've already reached the limits and no work needs to be done, so continue to the next iteration. Otherwise, implement the crux of the binary search querying implementation, which is to actually find the boundary tuples by asking membership queries. So the middle value between the current bounds of the interval were saved in the middle variable using the Boolean algebra low set get middle function, and then the transition from the current prefix, which was from the current prefix to this middle symbol, is then processed by similar methods to the pre-processing for the prefix, by making an arraylist prefix and adding the middle symbol to the end of it, and then processing and making the table cohesive so that you can find the state. So then middle order was defined with the middle symbol and the state of this transition, so that we can continue the loop in the same manner by having the order objects which are necessary. So if the state of the lower bound and the middle symbol are the same, that means that the boundary tuple does not lie between them, but lies between the middle symbol and the upper bound. So then set lower to middle order, so that when the next time comes around, we're looking at the interval from middle order to upper. And then otherwise, if the states are different, then it's the other way around, where the boundary tuple actually lies between lower and middle, the lower symbol and middle symbol, so then set upper to middle order. And then this loop is executed until the lower symbol and the upper symbol are adjacent to each other, i.e. until the next symbol after lower.c is actually upper.c, so the loop executes while this is not true. So as soon as this is true, the loop will stop, and we would have found the boundary tuple necessary. And then this loop is executed twice, one for the lower interval and one for the upper interval. And then that goes again. So that's binary search querying, and that wraps up all the base functionality that had to be implemented for this project. Now we shall move on to the additional challenging aspects that were implemented. The first of which was actually a custom partition functions implemented, which I called the middle partition, because it acts in the same way as the interval partition, except of how the boundaries of the intervals were defined. So it starts in the same way as the interval partition function, with the order object and the preds array initialized with the order being a number line of the symbols and their states. And so if the size of the order object is less or equal to 1, which means that there is 1 or 0 symbols, we have to handle the case where there's 1, because this is automatically handled in the interval partition function, but not for this implementation. So if there's only 1 symbol in the order thing, that means there was only 1 evidence symbol, then the predicate for that symbol's state is just the whole number line, essentially. So ba.true. Otherwise, actually implement the procedure described in the report, if you look at it. And so this pretty much, it took a turn on the interval partition function of, instead of defining the evidence symbols to be the actual boundaries of the intervals, the symbols in the middle between the two evidence symbols are actually the boundaries. So that is the only extra thing. So then we just got the middle values and did something very similar to the interval partition function by setting the predicates to the intervals between the middle symbols of adjacent evidence symbols rather than the evidence symbols themselves. And then the only edge cases is the first interval that would actually go from the minimum Boolean algebra symbol to the middle value between the first and second evidence symbols. And then at the end, for the last interval, it's actually from the middle value between the second to last and last evidence symbol and the maximum Boolean algebra symbol. So there's this loop pretty much just executes that by getting the middle, which actually is just a call to the BA low set get middle thing, but handles an edge case slightly differently and takes into account the order defined by the Boolean variable rev to make it able to process the custom partition function in the reverse order. So that was the first challenging aspect. The second challenging aspect was actually the investigating the benefits of applying the distributes procedure, which is described in just commenting out the code in learner.java in the make cohesive method. So this code was commented out to be able to test without applying the distribute procedure, and this was compared to the original benchmarks for the interval partition and binary search querying, which would have had the distribute procedure applied. And so yeah, that was the other bonus challenging aspect implemented. And so finally, moving on to the benchmarks, which are displayed in the report. So this was the result for the interval partition function. As can be seen, the least column is for the lexicographical least teacher, or which provides optimal counterexamples, and the random column is for the random teacher that provides random counterexamples. So you can see the interval partition function performs fairly well for optimal counterexamples, but does quite terribly for random examples, which are most not likely non-optimal at all. And so this is just due to how the interval partition function assumes the intervals to be defined, and so on. To remedy this, the binary search querying was implemented, and as can be seen, binary search querying off the bat, even with optimal counterexamples, performs less equivalence queries than without binary search querying. And for the random teacher with non-optimal counterexamples, it performs much better, being able to determine the intervals much more clearly by determining the boundary tuples using the binary search querying algorithm. However, it does require asking many more membership queries, as can be seen here, 887 and 900 compared to 281 and 586. So although it performs a lot better with equivalence queries, it does not perform as well for asking many more membership queries. But this is a good trade-off, because it means that the learner actually learns the SFA a lot faster with asking a lot less equivalence queries to the actual oracle, which is actually a desired trait in terms of performance of the learner. For the custom partition function, this was run without BSQ because that is how the code is implemented. So for the custom partition, we can see that it does not perform very well, because the reason that I implemented the middle partition function as described was to hopefully actually perform better for the random teacher, because it wouldn't assume that the non-optimal counterexamples were the boundaries, in which case they, because the non-optimal examples most likely weren't boundaries of the intervals. So hopefully that was going to remedy this, but as can be seen, it performs quite terribly for the optimal examples, as expected though, because it is trying to make provisions for non-optimal examples. However, for the non-optimal examples, it still does not perform too well, as it's roughly the same performance as the interval partition function for the random teacher. However, looking at the two equivalence queries for least and random side by side, you can see that it's quite consistent between the two. So that is actually somewhat of a benefit, is that there is consistency between the types of counterexamples provided. So it's kind of almost independent of the quality of the counterexamples provided. And that might be desirable if you have no idea what type of counterexamples you're going to get and you want consistent results. But overall, there does not seem to be as much of a benefit for using this custom partition function called the middle partition function against the interval partition function, especially if you know you're going to get optimal counterexamples. Finally, looking at the benchmarks results for applying versus not applying the distributes procedure, you can see when not applying the distributes procedure, there are more equivalence queries asked, but actually comparing it, if you were to look back, it actually tends to ask less membership queries for the least teacher and roughly the same amount of equivalence queries for the random teacher. So for optimal examples, if you want to save on membership queries, it would actually be better off not applying the distributes procedure, but if you want to get better equivalence queries, performing the distributes procedure is beneficial. So that is the main benefit for without BSQ, is that the distributes procedure saves on equivalence queries. And then with BSQ, it's mostly the same results, in that the number of equivalence queries goes down when using the distributes procedure versus when not using it. But when not using the distributes procedure, you actually save on membership queries, and this could be helpful for binary search querying, where binary search querying already increases the number of membership queries required by a substantial amount as opposed to not using it. So all in all, there is clearly a very good benefit of using the distributes procedure for saving equivalence queries and not having to ask as many equivalence queries as when not using the distributes procedure. But this comes at the cost of requiring more membership queries because of how the distributes procedure fills out the table more and requires the table to be filled out more with membership queries. And this about sums up the project implementation. Thank you so much for listening to me. And yeah, thank you.